It began with a question that seemed so simple it could fit inside a schoolbook. What keeps the moon from flying away? For centuries, the answer was a word every child learned early: gravity, the invisible pull that keeps the planets circling the sun and our feet pressed gently to the ground. Isaac Newton imagined it as a force reaching across the emptiness of space, acting instantaneously from one body to another, unseen but powerful enough to keep the cosmos in motion. For more than 200 years, that picture held firm. It explained falling apples, spinning planets, and the tides that rise and fall with the whisper of the moon. Then came Albert Einstein, a quiet man with wild hair and a habit of thinking in pictures instead of equations. He asked what that pull really was. If nothing could travel faster than light, how could gravity act instantly across the void? What if, he wondered, gravity was not a force at all, but a feature of space itself? In 1915, Einstein published his general theory of relativity, and with it, he changed the meaning of gravity forever. He revealed that mass does not tug on other mass through some invisible thread. Instead, it bends the stage on which everything moves. Space and time are not flat, empty backgrounds. They are soft, flexible, and curved. The sun bends space-time around it, and the Earth moves along the curves of that geometry. The planets do not circle because the sun pulls them. They fall freely through a curved landscape of space and time. Einstein once described it simply: matter tells space-time how to curve, and space-time tells matter how to move. That single sentence overturned Newton's centuries-old certainty. Gravity was no longer a mysterious pull. It was a manifestation of geometry itself. Imagine laying a heavy ball on a stretched rubber sheet. The sheet dips, and smaller marbles roll toward the heavy ball, not because they are pulled, but because the sheet's shape guides their paths. Now, replace the sheet with space-time itself, an invisible fabric that can stretch, twist, and warp, and you begin to glimpse Einstein's vision. Where there is mass, the fabric curves, and everything moving through it follows those curves. To us, that motion feels like gravity. Yet, in Einstein's universe, time is not separate from space. Together, they form a four-dimensional continuum, 3 dimensions of space and 1 of time, woven tightly into a single entity called space-time. You cannot move through space without also moving through time, and vice versa. The curvature of space-time does not only shape the paths of planets, it also changes the rhythm of time itself. This leads to one of the most haunting truths discovered in modern physics. Time itself flows differently depending on where you stand. A clock placed on a mountain ticks ever so slightly faster than a clock at sea level. Why? Because the mountain clock is farther from the center of Earth's mass, where space-time is less curved. In stronger gravity, closer to the mass, time slows. It is a tiny difference, barely measurable, but it is real. Astronauts on the International Space Station, floating higher above Earth's gravitational well, age microseconds faster than people on the ground. Over a lifetime, the difference is imperceptible, but it reminds us that gravity is not merely about space, it is about time itself. You can think of gravity as the stretching of time. The deeper you fall into a gravitational field, the slower time moves relative to distant regions where the curvature is weaker. Einstein showed that what we experience as a gravitational pull is, in essence, our natural motion through curved time. We fall not because something draws us downward, but because time itself bends in that direction. This idea seems almost too poetic to be true, and yet every experiment ever made confirms it. The Global Positioning System, those satellites orbiting above the Earth, must correct for time dilation caused both by their high speed and by the weaker gravity where they travel. Without those corrections, your phone's map would drift by several kilometers each day. Even technology depends on Einstein's geometry of time. But there is a question buried inside that revelation, one that Einstein himself may have smiled at but never fully answered. If gravity is a manifestation of curved space-time, And if time is part of that fabric, what would happen if time itself were to stop? If there were no flow of moments, no ticking of clocks, could space still curve? Could gravity exist at all? At first, it sounds absurd. How could time stop? Yet in the deepest reaches of physics, from the edge of black holes to the frozen equations of quantum gravity, time sometimes disappears from the mathematics altogether. That is where the paradox begins. Gravity shapes time, but time seems necessary for gravity to have meaning. Without time, there is no motion, no falling, no flow. The geometry may remain, but it would be a static, frozen landscape, curved perhaps, but lifeless. To say that gravity depends on time is to suggest something profound. Maybe gravity is not just the curvature of space, but the curvature of time itself. The bending of time gives rise to the experience of weight and fall. When we drop an object, we are not seeing a force in the Newtonian sense. We are witnessing time guiding matter along its most natural path. Einstein once compared spacetime to a fabric that tells matter how to move. But what if that fabric only exists because time gives it motion? If the film of the universe stopped playing, if every frame were frozen, would the curvature of spacetime still have meaning? Or is gravity an emergent effect of time's relentless forward march, a shadow cast by the flow of moments? Everyday experience offers hints. When you jump into the air, you rise and then fall, tracing a perfect arc. In that instant, your motion is not forced downward, it follows the curve of spacetime. But what gives that curve its direction, its arrow, is time. Time tells you which way is forward, and gravity tells you how that forwardness bends near mass. Without time's arrow, there is no way to define falling or rising. Everything would be static, suspended in an eternal stillness. The paradox deepens when you realize that acceleration itself is indistinguishable from gravity. Sit in a rocket accelerating through space, and the pressure you feel against your seat is identical to what you feel standing on Earth. Einstein called this the equivalence principle. It means that gravity and acceleration are two sides of the same reality, curved motion through spacetime. But motion requires time. Without time's flow, there is no acceleration, no equivalence, and therefore no gravity. So perhaps the question is not whether gravity exists, because time exists, but whether the two are simply different expressions of the same underlying truth. Time gives the universe sequence. Gravity gives it structure. Both might be the result of the same geometry, seen from different angles. To answer that, we must look backward in history, to a moment before Einstein, when even the idea of spacetime did not exist. A man named Hermann Minkowski, Einstein's former teacher, made a discovery that would set the foundation for all modern physics. He realized that space and time are not separate entities, but parts of one continuous four-dimensional reality. That insight became the mathematical language of Einstein's theory and changed how we understand the cosmos. To see whether gravity is born from time itself, we must revisit that birth, the moment when space and time were first woven together into a single fabric. And that story begins with Minkowski in the year 1908, when he declared to a startled audience that henceforth, space by itself and time by itself would fade into shadows, and only a union of the two would preserve an independent reality. Minkowski's statement struck many of his contemporaries as a mathematical curiosity rather than a revolution. To most physicists of the early 20th century, space and time were separate domains. Space, the vast stage upon which things moved, and time, the invisible metronome that ticked everywhere the same. Newton's equations required that separation. They assumed that space was absolute and unchanging, while time flowed evenly for all observers, unaffected by anything in the universe. Minkowski's claim shattered that certainty. He argued that every event in the universe could be described not by three coordinates of space and one of time, but by a single four-dimensional point in space-time. In this new geometry, An object's motion through space was inseparable from its motion through time. The faster something moved through space, the slower it moved through time. Even light itself, traveling at its ultimate speed, experienced no passage of time at all. Einstein quickly recognized that Minkowski's formulation was not just elegant, it was essential. It provided the mathematical skeleton for his general theory of relativity. Gravity, in this new language, was no longer a force acting through space, but a curvature in spacetime itself. The Earth orbits the Sun not because the Sun pulls it, but because the Sun's mass bends spacetime, and Earth follows the straightest possible path through that curved geometry, a path called a geodesic. Imagine drawing straight lines on the surface of a sphere. On a flat sheet, two straight lines can remain parallel forever, but on a curved surface, they eventually meet. Gravity works the same way. The geometry of spacetime is curved by mass and energy, and the straightest lines, those that represent free motion, appear to us as orbits, falls, or deflections. What we call gravitational attraction is simply the natural path of matter through a curved, four-dimensional continuum. This curvature does more than bend the motion of planets. It warps time itself. A second near a massive star is not the same as a second far from it. This was first confirmed in the mid-20th century, when precise atomic clocks placed at different altitudes showed that time flowed faster at higher elevations. Clocks on mountains ran ahead of clocks at sea level. To the human eye, such differences are invisible, but they are measurable, predictable, and utterly real. In a sense, we all live in stretched time. The deeper you are in a gravitational field, the slower your clock runs compared with those above you. From your own perspective, nothing changes. You never feel time slowing, but to someone higher up, you seem to move more slowly, speak more slowly, age more slowly. If you could hover just above the surface of a black hole, where gravity is extreme, an outside observer would see your time nearly frozen, while to you, moments would pass normally. This realization leads to an extraordinary thought. What we perceive as the strength of gravity might actually be a measure of how much time itself bends. Where time slows more dramatically, gravity feels stronger. Where time flows freely, gravity weakens. It is as though gravity is not pulling on us at all, but simply guiding us along the natural flow of time's curvature. Einstein's equations capture this relationship beautifully. They show that the distribution of mass and energy determines the curvature of spacetime, which in turn dictates how time flows. If a massive object like a planet is removed from a region of space, the curvature flattens and time flows more evenly. If more mass is added, time stretches and slows. Gravity and time are two interlocked aspects of the same geometric dance. Light itself obeys this curvature. When it passes near a massive body, its path bends. This bending was first observed during the solar eclipse of 1919, when astronomers measured starlight curving as it grazed the sun. The effect matched Einstein's predictions perfectly, transforming him overnight from an obscure theorist to a global icon. Yet what bent the light was not space alone, it was space-time. The photons, moving always forward at light speed, followed the geometry dictated by curved time as much as curved space. To picture this, imagine a river flowing through a valley. The water does not choose its path, it follows the shape of the land. The steeper the valley, the faster the flow. In the same way, the passage of time defines the slope that guides matter and light. Where time slows near mass, the flow bends inward. Gravity, in this sense, is the way matter moves along the contours of time itself. If this is true, then removing time from the universe would be like freezing the river's flow. Without that motion, nothing could follow a path, nothing could fall. The geometry might still exist, but it would be meaningless without the current of time to reveal its shape. This insight changes how we imagine reality itself. Instead of picturing gravity as a tug acting within a fixed stage, We see it as the stage's own motion, a choreography written in the language of time. When you drop a ball and watch it fall, you are witnessing not a force dragging it downward, but a small piece of space-time curving and the ball following that curve naturally. The ball's fall is time revealing its geometry. In a way, every moment of motion is an exchange between time and gravity. Time tells matter how to move, and matter tells time how to slow. Together, they create the fabric of experience, the feeling of weight, the rhythm of falling, the flow of days and nights. Remove either one, and the other ceases to make sense. Einstein's field equations tie this together mathematically, but the equations themselves whisper a philosophical truth. They tell us that the geometry of the universe is not static. It responds to mass, energy, and the passage of time. The universe is a living fabric, constantly reshaped by what it contains. Time is its pulse, and gravity is its shape. If you were to stand near a neutron star, where mass is crammed into a sphere barely 10 kilometers across, you would feel this relationship directly. Time there runs tens of thousands of times slower than on Earth. Gravity is not pulling harder in any Newtonian sense. Rather, time itself is flowing so unevenly that the natural paths through space-time all converge steeply inward. The star's gravity feels overwhelming because time is so distorted. Even the bending of light around galaxies, the phenomenon called gravitational lensing, can be seen as light obeying the gradients of time's flow. The light does not curve because something yanks it sideways. It follows the shortest route through a landscape where time moves differently at each point. The pattern we observe, the arc of distant starlight stretched across space, is a visible map of how time itself bends. Once we accept that, gravity is a manifestation of time's geometry, we face an inevitable question. If time were to slow completely, would gravity become infinite? If time were to stop, would gravity vanish altogether? These extremes are not merely philosophical. They exist in nature, in the strange hearts of black holes and the early moments of the universe. There, time's flow breaks down, and gravity behaves in ways that defy intuition. The link between time and gravity is not a metaphor. It is the most literal of relationships. Every experiment, every equation, and every observation points to the same conclusion. Where time flows unevenly, gravity appears. Without time's uneven flow, there would be no curvature to guide motion. The force we feel underfoot, the slow drift of planets, the orbits of stars, all arise because time is not uniform across the cosmos. To understand this relationship fully, we must explore what happens when time itself begins to fail. We must ask what it means for time to slow, and how that slowing gives rise to gravity's strength. Only then can we grasp why physicist Kip Thorne once said that gravity is the curvature of time. The next step is to look deeper into that slowing of time, to see how gravitational potential and the passage of moments are intertwined. For in the end, to fall is to follow time's gradient, and where time slows most profoundly, gravity grows strongest. The deeper we venture into the understanding of gravity, the more it becomes clear that the experience of falling is not caused by some mysterious downward pull, but by the shape of time itself. When you stand still on the surface of the Earth, you are actually being pushed upward by the ground beneath you, preventing you from following your natural trajectory through curved space-time. In freefall, on the other hand, you are doing exactly what space-time's geometry dictates, moving effortlessly along its curves. From this perspective, astronauts floating inside a spacecraft orbiting the planet are not weightless because gravity disappears, but because they are surrendering fully to the curvature of time. Gravitational potential, the familiar concept describing how much energy it takes to move an object from one height to another, can be seen as a measure of how much time itself slows at different locations. The deeper you descend into a gravitational well, the slower your clock ticks compared to one farther away. It is as though time thickens around massive bodies, creating a gradient that defines what we call gravity. When you walk uphill, You are not just climbing through space, you are moving through regions of slightly faster time. When you descend, you move into slower time. This is not metaphorical, it is measurable. The curvature of time produces the same effects that Newton once attributed to a force. Physicist Kip Thorne, one of Einstein's intellectual heirs, captured this elegantly when he said that gravity is the curvature of time. In his view, every fall, every orbit, every tug we feel is the result of time flowing unevenly across the universe. The closer you move toward mass, the more time stretches. When you drop a stone, it follows the gradient of that stretch, moving toward where time runs slower. In that sense, all motion under gravity is a migration through the landscape of time. If we could somehow visualize this, we might see time as a river flowing unevenly through the cosmos, its current slowed near massive objects and racing freely in empty space. Objects drift along that current. A planet circling a star is not trapped by a force. It is surfing the bends of time's flow. The stronger the curvature, the tighter the orbit, the deeper the sensation of weight. On the surface of Earth, our bodies resist this flow because the ground stops us from moving inward. The pressure we call weight is the resistance to the natural motion through curved time. This understanding leads to a remarkable insight. Acceleration and gravity are indistinguishable because both describe movement through time's geometry. When an elevator rises, you feel pressed to the floor. When it falls, you feel momentarily free. Both sensations are the result of how time flows relative to you. Remove time's flow entirely, and acceleration loses meaning. In a timeless universe, there would be no change, no motion, no fall. Gravity, being the manifestation of motion through curved time, would cease to exist. It is difficult to imagine a reality without time, because every experience we have depends on its flow. Yet physics forces us to confront that possibility. Near the boundary of a black hole, for example, time slows so drastically that from the viewpoint of a distant observer, it nearly halts. To someone falling toward that region, everything seems normal, but from outside, their descent appears to freeze. Gravity there grows unimaginably strong because the flow of time is almost completely suppressed. The closer you approach the point where time stops, the more intense gravity becomes. It is as though gravity is born from time's struggle to move forward. This relationship hints at a deeper truth. Time and gravity might not just influence one another, they might be two aspects of a single phenomenon. When we talk about the curvature of space-time, we are really describing how time itself bends around mass and energy. The curvature of space alone cannot create the sensation of gravity. It is the distortion of time, the slowing of its flow, that gives gravity its presence. Without time, the geometry of the universe would remain static and meaningless, an empty stage with no actors and no motion. Consider the simple act of dropping an apple. In Newton's picture, a force pulls it downward. In Einstein's, the apple follows the curvature of space-time. But in the deepest interpretation, what we truly see is the apple moving along the direction where time passes most slowly. The ground is the region of slower time, and the apple's fall is its journey toward that temporal depth. When it hits the ground, it stops not because a force ends, but because it has reached a point where time's gradient flattens and the surface resists further motion. This way of seeing gravity transforms the universe from a collection of forces into a vast network of time gradients. Every mass, from a grain of sand to a galaxy, reshapes the rhythm of time around it. The patterns of those rhythms define the structure of the cosmos. If you could somehow map the rate at which time flows everywhere, you would have a perfect picture of the gravitational field. The valleys of slow time would correspond to strong gravity, while the planes of uniform time would mark the emptiness between stars. We experience this structure constantly without realizing it. When you stand still, the ground beneath your feet is actually accelerating upward through space-time to keep you from following the natural curve of time. The sensation of weight you feel is the result of that upward acceleration relative to the local flow of time. If the ground were to vanish, you would no longer feel heavy because you would be moving freely along the flow of time's curvature. Einstein's theory allows us to calculate this relationship precisely. In his equations, the components that describe how time slows near mass are directly responsible for what we perceive as gravitational attraction. The stronger the time distortion, the stronger the apparent pull. This means that gravity is not an additional ingredient in the universe. It is a property of time's geometry. Remove that geometry, and gravity disappears naturally. But why does time bend around mass at all? The answer lies in the energy content of the universe. Mass and energy tell space-time how to curve, and that curvature dictates how time flows. When energy is concentrated, as in a planet or a star, space-time responds by slowing time near the source. The effect is not caused by a physical influence spreading outward, but by the very structure of reality adjusting itself to accommodate the presence of energy. Gravity, then, is the visible consequence of this adjustment. If time were uniform everywhere, the universe would be perfectly flat. Objects would move in straight lines forever, and there would be no attraction or fall. The diversity of motion we observe, the clustering of galaxies, the dance of moons, the orbits of planets, arises because time refuses to flow evenly. It bends and stretches, creating the dynamic architecture we inhabit. The connection between time's flow and gravity's strength becomes even more apparent when we study black holes. These cosmic abysses are places where time itself nearly stops relative to the outside world. Their immense mass compresses space-time so drastically that the direction of time tilts inward, pointing toward the singularity at the center. Everything, including light, must move along that tilt. From afar, we see the boundary where time stands still as the event horizon. Beyond it, even the concept of falling loses meaning because time ceases to exist in any familiar way. Such extremes remind us that gravity's power depends entirely on time's behavior. When time slows, gravity grows. When time halts, gravity becomes absolute. In that sense, the two are inseparable. To speak of one without the other is to miss half the picture. The universe itself may owe its structure to the interplay between them. A cosmic balance in which time shapes gravity and gravity sculpts time. Physicists continue to explore this relationship through experiments that measure the tiniest differences in clock rates between different altitudes or in the presence of varying gravitational strengths. Each measurement confirms the same principle. Wherever time flows unevenly, gravity reveals itself. The two cannot be separated by theory or observation, and so the paradox remains. Gravity shapes time, and time creates gravity. Which comes first? The answer may not lie in classical physics at all, but in the strange territory where thermodynamics and quantum mechanics meet, the place where the fabric of space-time begins to resemble a living system with memory and heat. To understand that, we must look at how energy, entropy, and the arrow of time combine to produce the geometry we call gravity. At the dawn of the 20th century, physics stood at a crossroads. The laws that had guided scientists since Newton seemed unshakable, describing with precision how objects moved and how forces acted upon them. Yet cracks had begun to appear in that grand structure. The strange behavior of light, the mysterious results of the Michelson and Morley experiment, and the discovery that nothing could travel faster than light forced thinkers to question what space and time really were. Out of this turmoil rose a new understanding, one so radical that it redefined the universe itself. In 1908, Hermann Minkowski, once Einstein's mathematics professor, stood before an audience in Cologne and declared that space and time, once thought to be separate, were in fact one and the same entity. He called this new concept space-time, a four-dimensional continuum that united the three familiar directions of space with the invisible direction of time. To most of his listeners, it sounded abstract, a mathematical trick to simplify equations. Few realized They were witnessing the birth of a new reality. Einstein soon recognized that Minkowski's vision was not just elegant, but essential. When he developed his general theory of relativity, space-time became the stage upon which all physical events unfolded. Space and time were no longer independent backdrops, but active participants in the cosmic drama. Every object, every beam of light, every atom followed paths determined by the geometry of space-time, and that geometry, in turn, was shaped by the distribution of matter and energy. Einstein expressed this relationship in his field equations, compact symbols that carry the weight of the universe. Matter tells space-time how to curve, and space-time tells matter how to move. This reciprocity means that gravity, the most familiar of forces, is not a force at all. It is the manifestation of space-time's curvature. The Earth orbits the Sun because the Sun's mass warps space-time around it, and Earth follows the straightest possible path within that curved geometry, a geodesic in 4 dimensions. This idea is difficult to visualize because our senses are built to perceive only 3 dimensions. We can picture a planet circling a star in space, but the time component is harder to grasp. Yet it is precisely this 4th dimension that gives the geometry its meaning. A geodesic is not a line in space, but a trajectory in space-time, a record of how an object moves through both space and time simultaneously. When space-time curves, that trajectory bends, and what we see as acceleration or attraction is simply the geometry revealing itself. To bring this to life, imagine a traveler moving through the cosmos. As they drift near a massive star, their path bends inward. To them, it feels like being pulled, but in truth, they are moving straight through a curved space-time. Their clock slows as they approach the star because the geometry of time itself is warped. The deeper they move into the gravitational well, the more time stretches. It is not just space that curves. Time does too. The sensation of gravity arises from this curvature of time. This insight was confirmed through observation. Astronomers found that clocks placed at higher altitudes ticked faster than those closer to Earth's center. Time, it seemed, depended on gravity. The stronger the gravitational field, the slower the passage of time. This phenomenon, called gravitational time dilation, lies at the heart of modern physics. It explains why satellites in orbit must adjust their onboard clocks to match those on the ground. Without that correction, navigation systems would drift and fail. Light itself is not immune to spacetime's curvature. When a beam of light passes near a massive object, its path bends, not because it is pulled, but because it follows the shortest route through curved spacetime. This was dramatically confirmed during the solar eclipse of 1919, when starlight passing near the Sun appeared displaced. The universe had curved the path of light, exactly as Einstein predicted. That observation turned relativity from speculation into triumph. The curvature of spacetime also explains why time slows near massive bodies. In Einstein's equations, the components that describe the geometry of time are directly linked to gravitational potential. A clock near a massive object runs slower because time itself is stretched by the curvature. This slowing is not an illusion. It is a measurable difference that defines the strength of gravity. Where time bends more sharply, gravity feels stronger. Where time flows freely, gravity fades. From this perspective, gravity is not a tug, but a texture, a pattern woven into the fabric of space-time by the presence of mass and energy. If we could see the universe in 4 dimensions, we would not see planets pulled by invisible forces. We would see them gliding effortlessly along the curved surfaces of time and space, following paths as natural as raindrops sliding down a leaf. Minkowski's 4-dimensional vision made this possible. By merging space and time, he gave physicists a way to describe motion, causality, and gravity as aspects of one continuum. Before him, time had been a universal stage, the same everywhere. After him, time became local, mutable, responsive. Its flow could change from place to place, depending on the distribution of matter. This unity of space and time also resolved puzzles that had haunted physics. Light, which always travels at the same speed, became the anchor of spacetime's geometry. No matter how fast you move, light's speed remains constant, forcing space and time to adjust so that the total structure, the space-time interval, stays the same. What changes is not the distance or the duration separately, but their combination. This constancy weaves together the universe's geometry, ensuring that all observers, no matter their motion, describe the same underlying reality. Einstein saw beauty in this symmetry. He understood that the laws of physics should look the same for all observers, whether they are moving or stationary. Spacetime makes this possible. It provides a universal framework in which motion, energy, and gravity can coexist without contradiction. But there is more to the story than mathematics. Spacetime does not merely describe where and when events happen, it defines what is possible. Its curvature determines which paths objects can take, which directions time can flow, and even whether two events can influence each other. The structure of spacetime is the architecture of reality itself. When we say that matter tells spacetime how to curve, we mean that every bit of mass or energy leaves a mark on the geometry around it. A single particle changes the shape of spacetime ever so slightly. A planet creates a deep well. A star warps it dramatically. The collective effect of all these curvatures is the grand tapestry of the cosmos, a living structure that evolves as stars are born, live, and die. Yet this dynamic universe depends on the existence of time. The equations of relativity describe how spacetime curves. But that curvature only has meaning if time flows. Without time, there would be no motion, no evolution, no change in the geometry. The fabric would freeze, and gravity would lose its essence. To say that gravity is the curvature of spacetime is therefore only half the truth. The deeper truth is that it is the curvature of time that gives rise to what we perceive as gravity. The way time slows near mass, the way it stretches in the presence of energy, is what creates the experience of falling and weight. Time's distortion is not a side effect, it is the cause. This insight reshapes our understanding of everything from planetary motion to black holes. In regions of extreme gravity, time can slow so dramatically that from an outside perspective, it nearly stops. Inside those regions, the geometry of time becomes so curved that it points inward, trapping everything, even light. The event horizon of a black hole is not just a boundary in space, it is a boundary in time. If we follow this reasoning, we begin to see that gravity and time are inseparable. One cannot exist without the other. Gravity defines how time flows, and time defines how gravity acts. This interdependence suggests that the universe's structure is not built from space alone, but from the rhythm of time itself. The strength of gravity is a measure of how much time has been distorted. As we explore deeper into relativity, we find that the flow of time governs the behavior of everything, from the smallest particle to the largest galaxy. Each tick of a clock is a whisper of spacetime's geometry, a reminder that time and gravity are two sides of the same cosmic coin. To uncover why this relationship exists and how it shapes the universe, we must ask a new question. If time flows unevenly because of gravity, what happens in regions where time nearly stops? Does gravity grow stronger because time slows, or does time slow because gravity grows stronger? The two seem inseparable, bound by an equation that may hold the key to understanding the universe itself. To approach that key, we must look beyond geometry to the thermodynamics of spacetime, the strange idea that the laws governing heat and entropy may also govern gravity. For it is there, in the relationship between energy, information, and the arrow of time, that the true origin of gravity may be found. Minkowski's unification of space and time into a single fabric gave physicists a new lens through which to view the universe. but it also introduced a subtle philosophical shift that many did not grasp at first. If time and space are intertwined, then the flow of time is not an external rhythm imposed upon the cosmos. It is built into the very structure of reality. Every point in space-time carries its own local clock, ticking at its own rate, influenced by the geometry around it. The universe, once imagined as a rigid stage on which matter played, became a flexible, living structure whose shape defines the behavior of everything within it. To picture this, imagine space-time as a great invisible ocean, stretching endlessly. Waves and currents ripple through it wherever mass and energy reside. Planets, stars, and galaxies are not separate from this ocean. They are part of its motion. Their presence changes how it flows, and the ocean's flow guides their paths. Space and time are no longer containers. They are participants in a cosmic dance that has no fixed background. This realization leads to one of the most beautiful symmetries in physics. If matter shapes time and space, then motion through time and space determines how matter behaves. The relationship is perfectly mutual. The geometry of space-time tells matter how to move along its curves, and that motion in turn alters the geometry. The universe evolves through this continuous feedback loop, a self-sustaining interplay between matter and geometry. Einstein's field equations capture this interplay with mathematical precision. On one side of the equation lies geometry, the curvature of space-time. On the other side lies energy and momentum, the content of matter and radiation. They are equal, inseparable. The presence of energy dictates the curvature, and that curvature dictates the motion of energy. It is as though the universe constantly negotiates between its contents and its shape, adjusting moment by moment to maintain balance. But what gives geometry physical meaning is the dimension of time. Without time, the equations would describe a static sculpture, frozen and lifeless. Time turns geometry into motion, potential into reality. It allows curvature to evolve and matter to move. When time flows, the universe breathes. Einstein's insight also revealed that time is not universal. Every observer carries their own clock, and those clocks do not always agree. This relativity of time means that the universe does not have a single, shared present. Instead, each observer experiences their own local now, defined by their position and motion through space-time. Two events that seem simultaneous to one observer may occur at different times for another. There is no cosmic master clock keeping perfect time for all. This relativity of simultaneity changes everything. It means that the past, present, and future are not separate layers stacked neatly in order, but parts of a continuous, four-dimensional fabric. All events, those we call past, those we call future, exist as regions within space-time. We move through them, tracing our own world lines, carving out a path through the geometry of existence. In this picture, time does not flow like a river. Instead, it is we who move through the landscape of time. The curvature of space-time defines the shape of that landscape. Near massive objects, the geometry bends, stretching the local structure of time. An observer close to a massive planet moves through a region of space-time where time's direction tilts inward. This tilt is what we feel as gravity. It is not that something pulls us toward the planet, but that time itself points in that direction. When you drop a ball, it is simply following the flow of time's curvature, moving toward where time runs slower. This way of thinking redefines not only motion, but cause and effect. In Newtonian physics, forces acted across space, transmitting influence instantly. In relativity, causality is preserved through the structure of space-time. No signal or event can travel faster than light, because light defines the limit of causal connection. The geometry of space-time ensures that every cause leads to an effect only within a region allowed by its curvature. Outside that region, no influence can reach. Time and space work together to guard the universe's order. From this structure arises an elegant picture of reality. Every particle, and every planet traces a world line through space-time, a record of its existence from birth to death. The bending of those world lines reveals the curvature of space-time itself. Gravity is simply the pattern of those curves, the choreography of motion through a four-dimensional landscape. This description might sound abstract, but it has tangible consequences. Consider light again. When it passes near a massive object, it follows a curved path, not because light has weight, but because space-time itself bends. In extreme cases, like near a black hole, this bending can become so severe that light orbits the mass or even becomes trapped entirely. The paths of photons around such an object draw the contours of space-time, revealing its shape to distant observers. This bending of light also slows it down from the viewpoint of a distant observer. Not in the sense of changing its speed through space, it always travels at the same fundamental speed, but in the sense that time itself slows where gravity is strong. The light's journey through curved time appears stretched, delayed. This is why signals from distant pulsars or spacecraft shift in frequency as they move through varying gravitational fields. The light is not tired, time is. As we contemplate this, it becomes clear that the geometry of space-time is not an abstraction to be drawn on chalkboards. It is the universe itself. Every second that passes, every orbit, every wave of light is a manifestation of that geometry. Without it, motion and causality would vanish. The concept of space-time also explains why there can be no true separation between energy and geometry. Energy bends space-time, and the bending of space-time guides energy. This mutual dependency ensures that the universe is self-consistent. Even vacuum, the apparent emptiness between stars, possesses structure. Quantum fields ripple through it, and their energy contributes, however slightly, to the curvature of space-time. There is no such thing as truly empty space. Einstein's universe, therefore, is not made of matter drifting through a void, but of a fabric woven from the threads of space and time, vibrating with energy and curvature. Every particle, every beam of light, every ripple of gravity is part of that tapestry. Gravity is not a separate entity acting upon it. It is the texture of the fabric itself. If you could somehow pause the universe for an instant, freeze every motion, every vibration, you would not stop gravity. Instead, you would stop time, and with it, you would remove the very meaning of gravity. Curvature without time is like a melody without rhythm, beautiful in concept, but silent in reality. The experience of gravity requires time's flow, for it is through time that motion occurs and curvature expresses itself. This brings us to an even deeper question. If gravity is inseparable from time, what does that say about the origin of time itself? Does time exist because of gravity's curvature, or does curvature exist because of time's flow? It is a question that pushes the limits of general relativity, reaching toward the realm of thermodynamics and quantum physics, where time takes on a new and mysterious role. To uncover that mystery, we must explore how the fabric of space-time might emerge from something even more fundamental. How temperature, entropy, and the arrow of time might give rise to the geometry we call gravity. For in the end, perhaps gravity is not the foundation of the universe at all, but a byproduct of time's inexorable flow. Minkowski's revelation reshaped the universe into a single four-dimensional continuum, but Einstein's equations gave that continuum life. With them, space-time ceased to be a mere mathematical framework and became a dynamic physical entity capable of stretching, twisting, and rippling. The discovery carried implications so vast that more than a century later, we are still unraveling them. One of the most striking of these implications is that space-time is not static. It can evolve. When matter moves or energy flows, the geometry of space-time changes. This is not an instantaneous adjustment, but a propagation, like the ripples that spread when a stone strikes the surface of a pond. These ripples are gravitational waves, faint undulations of spacetime itself, predicted by Einstein in 1916 and finally observed a century later by the Laser Interferometer Gravitational Wave Observatory. They confirmed that spacetime is not a fixed background, but a living medium. This discovery marked a profound philosophical shift. In Newton's view, the universe was like a grand clockwork machine, its parts moving within a rigid stage of space and time. In Einstein's universe, the stage itself moves and responds. It is as if the universe has awareness of its contents, not in a conscious sense, but in the way a stretched fabric knows where it has been touched. Each star, each planet, each speck of dust impresses its existence upon space-time, and space-time answers by reshaping itself. The idea that space and time can ripple and curve forces us to rethink what existence means. If the geometry of the universe is not merely a backdrop, but a participant, then everything that happens is a dialogue between matter and the fabric that contains it. The orbit of a planet is not imposed from outside. It emerges naturally from this dialogue. In the same way, gravity is not an added influence. It is the expression of spacetime's response to energy. At the heart of Einstein's theory lies a principle called covariance, which means that the laws of physics take the same form in all frames of reference. There is no privileged viewpoint, no universal stage upon which events unfold. Instead, every observer, wherever and whenever they are, measures the universe according to their own clock and ruler. This principle ensures that reality is consistent even though time and space appear different to each observer. From this relativity arises one of the most curious and profound consequences. The experience of time itself depends on gravity. The flow of moments, which feels so constant and absolute to human perception, is in fact elastic. It stretches near mass and contracts in emptiness. The deeper we fall into a gravitational field, the slower our seconds become relative to those farther away. This is not simply a poetic idea, it is the literal behavior of time in the universe. For instance, if two identical clocks are synchronized and one is placed on a mountain while the other remains at sea level, the mountain clock will tick faster. The difference may be tiny, a fraction of a billionth of a second, but it accumulates, and we must correct for it in technologies that rely on precision. This is how relativity reaches into our daily lives, subtly altering the timing of satellites and the flow of digital maps that guide our movements. This effect reveals something extraordinary. Gravity and time dilation are not separate phenomena, they are two sides of the same coin. The slowing of time near mass is what we experience as gravitational attraction. Objects move toward regions where time runs slower because those are the natural paths in curved spacetime. The sensation of falling, the pull we associate with weight, arises because time bends. Imagine standing at the edge of a great cosmic waterfall. The flow of time is like the water streaming endlessly downward. The stronger the gravitational field, the steeper the flow. Near a massive planet or a black hole, the current of time becomes so steep that even light cannot climb out. To resist that flow, an object must accelerate upward. What we call weight is simply the effort to stay still in a universe where time is always flowing downward. This picture offers a new way to understand why gravity cannot be separated from time. If time were to stop flowing, there would be no direction for motion, no way for matter to follow its natural paths. Space-time's curvature would become meaningless without the progression of moments. The very concept of cause and effect would vanish. Gravity requires time because it is defined by how matter moves through the geometry of time. The link between gravity and time also provides insight into one of the most puzzling questions in physics. Why does the universe have an arrow of time? We experience time as moving forward, from past to future. But the fundamental laws of physics do not require that direction. The equations work equally well if time runs backward. What gives time its direction may be the same thing that gives gravity its meaning. The asymmetry between regions of different curvature, the gradients of entropy that mark the passage from order to disorder. Einstein's equations describe how space-time curves, but they do not explain why curvature arises from deeper principles. To find that explanation, we must look beyond geometry, toward the realm of thermodynamics, the study of heat, energy, and entropy. It was there, in the mid-1990s, that physicist Ted Jacobson discovered something remarkable. The equations of general relativity can be derived from the laws of thermodynamics themselves. Jacobson's insight began with a question: what if space-time, like a gas or a liquid, possesses a kind of microscopic structure? If it does, then perhaps its large-scale behavior, curvature, motion, and gravity might emerge from statistical rules governing that structure. By examining how energy flows across a surface in space-time and how that flow relates to changes in entropy, Jacobson showed that Einstein's equations naturally arise as an equation of state. In thermodynamics, an equation of state describes how a system's pressure, temperature, and volume are related. Jacobson proposed that space-time behaves similarly. Its curvature corresponds to temperature, its energy content corresponds to pressure, and its geometry adjusts to maintain equilibrium. In this view, gravity is not a fundamental force, but a manifestation of the thermodynamic behavior of space-time. This interpretation carries profound implications. Entropy, the measure of disorder or information, requires time to have meaning. It increases as time moves forward, marking the arrow of time we perceive. If Einstein's equations can be derived from thermodynamic principles, then the existence of gravity depends on the existence of time's arrow. Without time, there can be no change in entropy, and without that change, there can be no curvature, no gravity. Jacobson summarized it beautifully. The Einstein equation is the equation of state of space-time. It describes not a fundamental law, but a condition that arises from the collective behavior of underlying microscopic degrees of freedom. Gravity, in this sense, is emergent, a property that appears only when we observe the universe at scales where time and entropy are meaningful. This perspective ties together everything we have explored. Space and time form the stage, but the play itself, the motion, the curvature, the feeling of weight, arises from the thermodynamic flow of energy and information through that stage. Time's arrow gives rise to entropy. Entropy shapes curvature, and curvature becomes gravity. If we could freeze time, entropy would stop increasing. The microscopic fluctuations that give space-time its texture would cease. Without those fluctuations, the geometry would flatten, and gravity would vanish. The universe would become a static crystal of frozen possibilities. In the light of this understanding, the question that began our journey, does gravity exist only because time exists, gains new meaning. The evidence points toward yes. Time's flow allows entropy to grow, and entropy's growth gives space-time its curvature. Gravity is not the cause of time's passage, it is its consequence. In the chapters ahead, we will explore this connection more deeply, tracing how entropy, information, and the quantum nature of space-time intertwine. We will see how the geometry of time gives birth to the geometry of space, and how both may emerge from the invisible network of information that underlies reality itself. Gravity has always seemed like the most familiar of forces, the quiet companion of every moment of our lives. We feel it pressing against us as we stand, shaping the fall of rain, guiding the rise of tides. Yet the more closely we examine it, the more it becomes clear that gravity is not a force in the ordinary sense. It is the visible face of time itself. To understand why, imagine two identical clocks. Place one on the ground and lift the other to the top of a tall tower. Let them tick together for a while, then bring them back side by side. You will find that the clock from the tower has advanced slightly faster. It has lived through a fraction more time than the one that remained below. This difference is not a trick of mechanics, but a truth of nature. Time itself flows more slowly closer to mass. This phenomenon, called gravitational time dilation, is one of Einstein's most striking predictions, and it has been confirmed with exquisite precision. The flow of time depends on gravitational potential. The deeper you are in a gravitational field, the slower your seconds pass compared to those farther away. The difference is minuscule for everyday experiences, but it becomes profound near massive objects. If you were to hover just above the surface of a neutron star, time for you would slow to a crawl compared to a distant observer. A single second by your clock might correspond to hours or days for someone far away. Descend deeper still, toward the event horizon of a black hole, and the effect becomes extreme. From the outside, your motion would appear to freeze. Time would seem to stop. Yet from your own perspective, everything would continue as normal. This strange duality reveals something fundamental. The strength of gravity is not merely proportional to mass, it is proportional to the curvature of time. Where time bends sharply, gravity is strong. Where time flows freely, gravity weakens. The link is not metaphorical, it is mathematical. The components of Einstein's field equations that describe the rate at which time changes from place to place are the very same components that define gravitational acceleration. This means that when you drop an apple and watch it fall, it is not being pulled downward. Instead, it is following the natural curve of time, moving toward the region where time passes more slowly. The ground is the place where time runs slowest relative to the air above, and the apple's motion simply follows that gradient. What we call falling is the act of sliding down a slope in the landscape of time. To stand still on the ground, then, is to resist that slope. The ground pushes upward to keep you from following the natural curvature of time. The sensation of weight you feel in your feet is not the result of a force pulling you down, but of the surface beneath you, preventing your motion through time's geometry. If the ground were to vanish, you would no longer feel weight because you would be in free fall, gliding effortlessly along time's slope. Einstein once described this equivalence between free fall and weightlessness as one of the most beautiful ideas of his life. It led him to the realization that acceleration and gravity are indistinguishable. To an astronaut floating inside a spacecraft far from any planet, everything seems weightless. But if the spacecraft begins to accelerate, a feeling of gravity returns. The floor presses against their feet. Objects fall to the ground. Yet what they feel is not gravity in the Newtonian sense, but the resistance to acceleration through space-time. This equivalence principle reveals that gravity and acceleration are both manifestations of the same thing, curvature. But acceleration only makes sense in the presence of time. Without the passage of moments, there is no way to measure change in velocity, no sense of motion at all. Time is the canvas upon which both acceleration and gravity are painted. Remove time, and both vanish instantly. The realization that gravity arises from time's curvature also explains why it cannot be shielded or blocked. You can insulate yourself from electricity with rubber, from magnetism with metal, from radiation with lead, but you cannot hide from gravity. Wherever you are, time flows, and as long as it flows unevenly, you will feel gravity's presence. It is not an external influence, it is the shape of reality itself. This understanding gives new meaning to the idea of gravitational potential. When physicists speak of potential energy, they usually refer to position, the height of an object in a gravitational field. But in the language of relativity, potential is better understood as a measure of time's rate. The higher you climb, the faster your clock ticks. The lower you descend, the slower it runs. The difference in those rates defines the potential difference that drives motion. Objects move from regions of slower time to regions of faster time, just as heat flows from hot to cold. In this view, the universe itself is filled with gradients of time. Every mass, from the smallest pebble to the largest galaxy, creates its own local distortion in the flow of moments. The geometry of those distortions forms a vast interconnected web. When you walk, jump, or fall, you are navigating that web. Every step you take shifts your position in the river of time, subtly altering your personal rhythm relative to the rest of the cosmos. Near massive bodies, these gradients become steep. Around a black hole, time is stretched so dramatically that its flow nearly halts at the horizon. From far away, you would see an object approach that boundary and slow indefinitely, its light redshifting to invisibility. From the object's own perspective, it would continue inward without pause, crossing into a region where the roles of space and time trade places. Inside the horizon, time points inexorably toward the center, and escape becomes impossible. This exchange of roles is more than a curiosity, it is a clue. It tells us that gravity and time are deeply intertwined, so much so that when one becomes extreme, the other transforms. Near the horizon, gravity becomes absolute because time loses its flow. Without time's direction, motion ceases to have meaning. Gravity, in its strongest form, marks the boundary where time dies. These insights challenge our ordinary perception of reality. We experience time as uniform, a steady rhythm that carries us from one moment to the next. Yet the universe reminds us constantly that time is not uniform. It bends and twists around mass and energy. Each second we live is part of a larger cosmic clock whose hands move at different speeds across different regions. The pull of gravity we feel is a symptom of this uneven flow. This view also reveals why gravity is universal. Everything that exists, from photons to galaxies, is embedded in the same fabric of time. No object can escape its influence, because no object can exist outside time. Even light, which moves at the cosmic speed limit, is not immune. Its path bends around stars because it follows the curvature of time as much as the curvature of space. The bending of light, or gravitational lensing, offers one of the most vivid illustrations of this relationship. When light from a distant galaxy passes near a massive cluster, its trajectory is deflected, producing arcs and rings in the sky. What we are seeing in those distortions is not light being pushed or pulled, but light tracing the contours of time's curvature. The lens is not a physical barrier, it is a gradient in the flow of moments. As we look deeper into the universe, we see these effects everywhere. The orbits of planets, the structure of galaxies, even the expansion of the cosmos itself are governed by how time stretches and compresses under the influence of gravity. The grand architecture of the universe is a map of time's geometry, sculpted by mass and energy over billions of years. But this understanding raises another profound question. If time's curvature creates gravity, what happens when time stops changing? Can gravity exist in a timeless universe? Or does its strength vanish with the end of time's flow? The search for that answer leads us beyond classical relativity into the realm of thermodynamics and quantum mechanics, where time and gravity might not just interact, but emerge together from deeper laws. In the next chapter, we will follow that thread into the heart of one of the most astonishing discoveries in modern physics, the realization that Einstein's equations themselves can arise from the thermodynamic behavior of spacetime. In that discovery lies a new truth, that gravity, like heat, may be an emergent phenomenon born from the arrow of time. The deeper we look into gravity, the clearer it becomes that its strength rises from the way time bends. In regions where time stretches and slows, gravity grows fierce. This is not speculation. It is written directly into the mathematics of relativity. Einstein's equations tell us that the curvature of space-time depends on the distribution of mass and energy, and that curvature dictates the passage of time. Where the geometry tightens, the flow of time thins. Gravitational potential, once thought of simply as a measure of height or position, now reveals itself as a measure of how differently time moves from one place to another. Imagine time as a vast field of invisible currents, flowing faster in some regions and slower in others. The deeper you move into a gravitational well, the slower the current becomes. Motion itself arises from this difference. Objects drift naturally towards slower time, just as rivers flow toward the sea. This connection is not limited to abstract equations. It can be observed. Modern atomic clocks, precise enough to measure billionths of a second, confirm that time runs faster, even a few meters higher above Earth's surface. Step onto a tall building, and your clock gains a fraction of a second over a lifetime compared to one kept in a basement. The difference is infinitesimal, but it tells a profound truth. Time itself defines the shape of gravity. We can trace this relationship in every corner of the cosmos. Near the surface of a neutron star, time runs tens of thousands of times slower than on Earth. At the edge of a black hole, the flow of time nearly stops altogether. From a distance, a falling object appears to freeze in place as it approaches the event horizon. Its image grows dimmer, stretched by the gravitational redshift, until it fades entirely. Yet from the object's own point of view, nothing strange happens. It continues smoothly through the horizon, unaware that from the outside, time itself has sealed it off from the universe. This paradox, time freezing from one view while flowing normally from another, reveals the dual nature of gravity. It is both the distortion of space and the deformation of time. But it is the temporal distortion that gives gravity its strength. If the rate of time were the same everywhere, space-time would be perfectly flat, and gravity would not exist. In this way, gravity can be seen as the universe's way of balancing time. Massive bodies create pockets where time slows, while empty space allows it to speed up. The gradient between these regions defines the curvature that shapes motion. The planets orbit the Sun because they follow paths where the flow of time naturally leads them. They are not held in place by invisible threads, but by the contours of time's geometry. Even light, though it has no mass, obeys these contours. When it travels through a gravitational field, it moves through regions where time runs differently, and its path bends accordingly. Light follows the shortest route through space-time, but that route is curved because time itself is uneven. The result is the gravitational lensing that astronomers observe when distant galaxies appear distorted around clusters of mass. Those arcs of light are not tricks of perspective. They are the visible fingerprints of time's bending. If gravity grows stronger where time slows, then the ultimate limit of gravity must occur where time stops completely. That is precisely what happens at the center of a black hole. There, according to relativity, time ceases to flow in any recognizable sense. All paths lead inward, and the direction we call forward in time becomes indistinguishable from down toward the singularity. Gravity's infinite strength and time's complete stillness are two sides of the same coin. When one becomes absolute, so does the other. This interdependence suggests a remarkable idea. Time may be the engine of gravity. The uneven flow of moments across the universe generates the curvature we interpret as gravitational attraction. Where time flows steadily, space remains flat and calm. Where time slows, curvature appears. The deeper the difference in temporal flow, the stronger the curvature and the more powerful the gravity. Kip Thorne captured this beautifully when he wrote that gravity is the curvature of time. In his description, an object in free fall moves along the direction where time passes most slowly. When you release an apple from your hand, it follows the gradient of time's flow. The ground, where time is slowest, marks the end of that path. The apple's motion is nothing more than time expressing its geometry. Seen this way, the universe becomes a vast map of temporal landscapes, with valleys and peaks defined by how fast or slow time moves. Every mass carves a depression in this map, pulling nearby matter toward its center. But unlike a landscape of rock and soil, this terrain is not made of substance, it is made of duration. Gravity is the shape of time itself. This perspective also helps explain why gravity cannot be separated from the flow of energy and entropy. Whenever mass or energy moves, it distorts space-time, changing how time passes in surrounding regions. Those distortions propagate outward as gravitational waves, ripples in the fabric of time. These waves carry information about their sources, allowing us to detect events billions of light-years away. The waves recorded by the Laser Interferometer, Gravitational Wave Observatory, are not disturbances in space alone. They are oscillations in time's rhythm, tiny tremors in the universe's heartbeat. The inseparability of time and gravity also imposes a natural order on the cosmos. The flow of time determines what can happen and in what sequence. Gravity ensures that this sequence remains consistent by shaping the structure through which time unfolds. Without gravity, time might lose its direction, dissolving into randomness. Without time, gravity would have no meaning, for curvature only exists when change can occur. As we approach the limits of relativity, we begin to see that this relationship is not just deep, it may be fundamental. If time were to lose its flow, gravity would fade. If gravity were to vanish, time might cease to have any direction. The two seem to rise together from a single underlying principle, one that connects the geometry of space-time with the thermodynamic arrow of time. This realization leads us toward a new horizon of thought. Could it be that gravity itself is not fundamental, but emergent, arising from the same microscopic processes that produce time's flow and entropy's growth? Could the curvature of space-time be a large-scale illusion, the collective effect of countless quantum interactions happening beneath our awareness? These questions drive modern physics toward a deeper understanding of reality. They suggest that to comprehend gravity fully, we must look not just at geometry, but at the hidden connections between energy, information, and time. The next step in our journey leads us there, to the thermodynamics of space-time, where gravity may emerge from the heat of existence itself. To understand why gravity deepens when time slows, we must look beneath the surface of Einstein's equations and into the strange connection between thermodynamics and space-time itself. For much of the 20th century, gravity was treated as purely geometric, a warping of space and time caused by mass and energy. But in the 1990s, a new insight emerged that shook that assumption. It suggested that the geometry of space-time might be nothing more than a large-scale shadow of microscopic processes, and that gravity could be born from the same principles that govern heat, temperature, and entropy. Physicist Ted Jacobson made this discovery in 1995. He began with a bold question. If space-time has energy, can it also have temperature? And if it has temperature, might it obey the same thermodynamic laws that describe gases and fluids? Jacobson imagined an observer hovering just above the surface of any small patch of space-time. For that observer, the boundary between regions of visibility and invisibility, a local horizon, would act like a thermal surface. Energy could flow across it, and that flow would produce changes in entropy, just as it does in any thermodynamic system. By applying the first law of thermodynamics, the rule that relates heat flow to changes in entropy and temperature, Jacobson showed something astonishing. When he expressed those relations mathematically and demanded that they hold for all possible local horizons, the resulting equations were exactly Einstein's field equations. Gravity, it seemed, could be derived not from geometry as a starting point, but from thermodynamics itself. This meant that Einstein's great theory might not be a fundamental description of reality at all. Instead, it might be an equation of state, a macroscopic law that emerges from countless microscopic interactions, just as the laws of pressure and temperature emerge from the random motions of atoms in a gas. In Jacobson's own words, the Einstein equation is the equation of state of space-time. This idea carries profound consequences. If gravity arises from thermodynamics, then it requires the existence of entropy, and entropy requires time. Entropy is the measure of how disorder increases as time moves forward. It gives the universe its arrow, the reason why you remember the past but not the future, why a glass can shatter but never spontaneously reassemble. Without the passage of time, entropy would not increase, and without that increase, the thermodynamic foundation of gravity would collapse. In other words, if time were to stop, the very mechanism that gives rise to curvature would vanish. Spacetime would no longer respond to energy. Gravity would cease to exist. The universe would freeze into an eternal equilibrium with no motion, no heat, and no change, a perfectly still, timeless expanse. Jacobson's insight united gravity and time in a new way. Einstein had shown that gravity shapes time, and time defines gravity's strength. Jacobson revealed that both may be manifestations of the same underlying thermodynamic process. Spacetime itself behaves like a fluid with temperature and entropy. When energy flows through it, its geometry shifts to maintain balance, and that shift appears to us as gravity. This framework also explains why horizons, boundaries where time slows dramatically, carry entropy. The event horizon of a black hole, for instance, behaves like a thermal surface, with temperature and entropy proportional to its area. When matter falls into a black hole, the horizon grows, and its entropy increases. Stephen Hawking's calculations in the 1970s showed that black holes emit radiation as if they were hot bodies, slowly losing mass as they radiate energy. The temperature of a black hole is inversely proportional to its mass. The smaller it is, the hotter it becomes. Hawking's discovery hinted that space-time possesses microscopic degrees of freedom, tiny quantum constituents whose collective behavior gives rise to temperature and entropy. Jacobson's work completed the circle by showing that those same microscopic processes can produce gravity as an emergent phenomenon. The curvature we see is the macroscopic manifestation of statistical rules governing the unseen structure of spacetime. This interpretation turns the universe into something more like a living system. Each region of spacetime exchanges energy and information with its surroundings, constantly adjusting its curvature to preserve equilibrium. Time's flow drives this exchange, ensuring that entropy always increases. Gravity becomes the thermal memory of time's passage, the way the universe records the irreversible flow from past to future. If we accept this view, then the strength of gravity in any region reflects how much entropy is encoded in its geometry. A massive star, dense and hot, bends spacetime sharply because it contains immense energy and therefore immense entropy. As that star collapses into a black hole, its entropy multiplies. The horizon that forms around it represents not just a boundary in space, but a surface of maximum information, a place where all the details of the star's interior are re-expressed as thermodynamic data on the horizon. This is more than a metaphor. The holographic principle, inspired by black hole physics, suggests that the amount of information that can be contained in a region of space is proportional not to its volume, but to the area of its boundary. This means that the entire content of a three-dimensional region could, in principle, be encoded on a two-dimensional surface surrounding it. Gravity, in this sense, is the way space-time organizes that information. Entropy, information, and time are thus inseparable from gravity. The arrow of time is the direction in which entropy increases. The increase of entropy defines how information spreads and changes, and that spreading, that constant redistribution of information across space-time, generates the curvature we experience as gravity. In a world without time, entropy could not change. Without that change, no information would flow. Space-time would lose its thermodynamic life, and the geometry of gravity would flatten into silence. Time's arrow gives rise to heat, heat gives rise to entropy, and entropy gives rise to gravity. The universe's weight is the echo of its irreversible motion through time. Jacobson's work opened the door to a new vision of physics, one in which time and gravity are not fundamental ingredients, but emergent patterns. The laws of thermodynamics, once confined to describing engines and gases, now seem to govern the very structure of spacetime itself. Einstein's geometry may be only the surface of a deeper reality. a reality woven from information, energy, and the flow of moments. If gravity truly emerges from thermodynamics, then we can no longer think of space-time as a passive stage. It becomes a dynamic, statistical medium whose properties depend on how information is distributed and how time unfolds. Each tick of a clock is a microscopic reshaping of that medium, a subtle adjustment in the cosmic balance between order and disorder. The implications are vast. It suggests that gravity, time, and even the fabric of reality might arise from the same underlying principle: the evolution of information. The next step in our exploration will take us there, into the realm of emergent gravity, where physicists like Eric Verlinde have proposed that the pull we feel toward the Earth is not fundamental at all, but the result of the universe's information adjusting itself as time flows forward. If Jacobson showed that gravity is the thermodynamics of time, Verlinde proposes that gravity is the geometry of information, a manifestation of entropy unfolding in motion. Together, their ideas paint a single cosmic picture: that time and gravity are inseparable because both emerge from the universe's drive to record, remember, and evolve. When Jacobson proposed that gravity arises from thermodynamics, he did not merely offer a new equation, he offered a new way to think about the universe itself. He was saying that space-time is not a static fabric stretched over nothingness, but a kind of medium that holds energy, information, and entropy. Its geometry is not simply drawn by matter. It evolves like heat spreading through metal, like air flowing through a room. In that view, gravity is not fundamental. It is a reflection of how space-time reacts when time moves forward. Entropy is the heart of this idea. Every physical system has entropy, a measure of how many ways its microscopic pieces can be arranged while still appearing the same on a large scale. The second law of thermodynamics tells us that entropy always increases with time. That increase defines the arrow of time itself. We know the difference between past and future because the universe's entropy grows. If entropy ever stopped increasing, time would lose its direction. Jacobson realized that this principle might not stop at atoms or stars. It might apply to the universe's geometry itself. Every region of space-time, every tiny patch of horizon, carries entropy. When energy flows across such a surface, entropy changes. If you demand that the first law of thermodynamics holds everywhere, that energy flow and entropy change always remain balanced, Einstein's equations appear automatically. Gravity becomes a thermodynamic necessity. That means the curvature of space-time, the slowing of time near mass, the bending of light, all emerge from the same underlying rule that governs a boiling kettle or a melting glacier. The universe obeys a grander thermodynamic law, and gravity is its visible consequence. This realization ties the existence of gravity directly to the existence of time. Entropy requires change. Change requires time. If time were to stop, no process could unfold, no energy could flow, no entropy could increase. The equations that give rise to gravity would become meaningless. Without time, space-time would lose the property that allows it to respond to energy. The universe would freeze in perfect balance. No curvature, no motion, no gravity. Seen this way, time is not just the stage on which gravity acts. It is the source that gives gravity meaning. The flow of time drives the growth of entropy, and entropy's growth shapes the curvature of space-time. Time does not merely coexist with gravity, it generates it. This connection becomes clearer when we look at black holes. The surface of a black hole, called the event horizon, behaves like a thermodynamic system. Stephen Hawking showed that black holes emit radiation with a temperature inversely related to their mass. They have entropy proportional to the area of their horizon. This entropy is not metaphorical, it is measurable. The horizon encodes the information about everything that has fallen into the black hole. When matter crosses the horizon, the area increases, and so does the entropy. The second law of thermodynamics, which governs all physical systems, extends to these cosmic giants. A black hole cannot decrease its total entropy without violating time's arrow. Even in the depths of gravity's strongest domain, time and entropy remain bound together. If entropy is information, then time is the universe's way of processing it. Each tick of a clock corresponds to a rearrangement of information. The flow of time is the flow of knowledge from order to disorder. Gravity, emerging from that flow, is the geometric expression of the universe's computation. Every curve in space-time, every orbit and wave, records the memory of entropy increasing. In this view, the Einstein equation is not a law of forces, but a balance sheet of information. The curvature of space-time keeps track of how energy moves and how entropy grows. Time's arrow writes itself into geometry, and the result is gravity. If this is true, then the universe itself is a thermodynamic system. Galaxies, stars, and black holes are its engines, converting energy into entropy. Gravity guides that conversion by shaping the flow of time. Without the uneven passage of moments, energy would never spread, entropy would never increase, and the universe would never evolve. Time is the mechanism by which the cosmos remembers. Even the cosmic expansion reflects this thermodynamic truth. The universe began in a state of extraordinary order, with energy and matter evenly distributed. Over billions of years, entropy has grown as structures formed and stars burned their fuel. Gravity played the central role in that transformation. It gathered matter into clumps, ignited stars, and sculpted galaxies. Every gravitational collapse increased the universe's entropy, deepening the arrow of time. This feedback loop is endless. Time drives entropy, entropy drives gravity, gravity drives cosmic evolution, which creates new pathways for entropy to increase. The universe is not a closed system drifting toward equilibrium. It is an unfolding process of continual reorganization. Gravity is the memory of that process written into the fabric of time. Jacobson's insight invites us to see space-time not as a fundamental stage, but as a collective phenomenon, like temperature in a gas. Temperature does not exist at the level of a single molecule. It emerges from the statistical behavior of many molecules. In the same way, space-time may not exist at the level of quantum reality. It may arise only when countless microscopic interactions average together to create the smooth geometry we experience. Gravity, then, is like heat. It is an emergent effect of underlying motion we cannot yet see. If this is true, the universe is made not of continuous space and time, but of discrete pieces of information interacting endlessly. Time's flow is the ordering of those interactions. Gravity is the macroscopic pattern they form. To glimpse this hidden order, we can look at the smallest possible scale, the Planck scale, where distances are about 10 to the power of minus 35 meters. At that scale, space-time itself is expected to fluctuate wildly, bubbling with quantum uncertainty. There is no smooth geometry there, no defined flow of time. What we perceive as curvature and gravity at larger scales may be the statistical average of those microscopic fluctuations. Entropy becomes the bridge between the quantum and the cosmic. It connects the tiny, random motions of quantum fields with the grand, continuous sweep of galaxies. Time translates those fluctuations into order, giving rise to the classical world. Gravity emerges as the geometry of that translation, a map of how information is exchanged as the universe evolves. If entropy did not exist, information could not spread. If information could not spread, there would be no difference between past and future. Without that difference, time would have no arrow. Without time's arrow, gravity would have no curvature. Thus, Jacobson's insight completes a chain that links the fundamental features of reality. Time gives rise to entropy. Entropy gives rise to curvature. Curvature gives rise to gravity. And gravity, in turn, shapes time. The cycle is perfect, self-sustaining, and cosmic. But this understanding also raises a new question. If gravity and time are both emergent, then they must share a common source. There must be something deeper, a principle beneath both geometry and thermodynamics, capable of giving rise to the flow of time and the pull of gravity together. To search for that principle, we turn to the idea of emergent gravity proposed by Erik Verlinde. He suggests that gravity is not only thermodynamic, but informational, that it arises from changes in the universe's information content. In his view, the force we feel as gravity is not fundamental at all. It is the entropic tendency of spacetime to reorganize its information as time progresses. If Jacobson showed that gravity is the thermodynamics of time, Verlinde shows that it is the geometry of information. Together, they lead to a startling thought. Perhaps gravity is nothing but time, seen from the perspective of information itself. When Erik Verlinde introduced the idea of emergent gravity in 2010, he took Jacobson's insight and pushed it further. He asked what would happen if spacetime itself were not a fundamental arena, but a large-scale manifestation of information. In his view, the geometry that Einstein described, the curvature that we call gravity, could be the result of microscopic changes in how information is stored and organized throughout the universe. Verlinde proposed that gravity arises not because masses attract one another, but because the universe strives to increase its entropy. He compared this to an entropic force, like the one that makes a stretched rubber band contract. When you stretch the band, you reduce its entropy. It resists that change, pulling back toward equilibrium. Verlinde suggested that gravity works the same way. When matter moves, it changes the information structure of spacetime, and spacetime responds by restoring equilibrium. The result is the force we feel as gravity. This idea transforms gravity from a geometric property into an informational one. In Verlinde's universe, every region of spacetime contains a certain number of bits of information, encoded in the positions and states of its fundamental constituents. The distribution of that information determines how time flows and how curvature appears. When matter moves, it shifts the balance of information, creating an entropic gradient. Matter then moves downhill along that gradient, following the path that increases entropy most efficiently. That motion, observed from within the universe, appears to be gravitational attraction. Entropy and time once again stand at the center of this picture. Entropy can only increase if time flows, and gravity only manifests if entropy increases. The three form a perfect triad. Time enables entropy generates gravity, and gravity gives time its structure. To make this more concrete, imagine a planet orbiting a star. In Newtonian physics, the star pulls on the planet through a gravitational force. In Einstein's geometry, the planet follows a curved path through spacetime. In Verlinde's entropic framework, the planet moves because the information in spacetime changes as it shifts position. The entropy of the surrounding space increases when the planet moves toward the star, and that increase defines the direction of time's arrow. In this sense, time is not merely the dimension through which motion occurs, it is the record of how information rearranges itself. Each moment is a new configuration of the universe's information content. Gravity emerges as the tendency for those configurations to evolve towards states of higher entropy. This interpretation gives a natural explanation for why gravity is universal. Every physical system carries information, and every change in that information affects the surrounding spacetime. There is no way to isolate one system completely from another, because all information is part of the same cosmic network. Gravity is the universal bookkeeping that ensures the balance of information and energy remains consistent as time unfolds. If spacetime is made of information, then the flow of time corresponds to the evolution of that information. Time does not move independently. It is the ordering principle that turns the static data of the universe into a dynamic story. Without the progression of information, there would be no difference between one moment and the next. the universe would be frozen in a single configuration, devoid of gravity, motion, and change. This picture aligns with ideas emerging from quantum gravity and the holographic principle. The holographic view of the universe suggests that all the information contained within a region of space can be described by data encoded on its boundary. The interior is not independent. It is the projection of that boundary information into higher dimensions. In such a framework, spacetime and gravity become emergent properties of information itself. The geometry we perceive is a translation of how quantum bits are entangled and organized. If the shape of spacetime reflects the pattern of information, then time is the process by which those patterns change. The curvature that we identify as gravity is the visible trace of that change. As information rearranges itself to increase entropy, time flows and gravity appears. Verlinder's model finds support in cosmological observations. When he applied his framework to the rotation of galaxies, he found that it could reproduce the same effects that astrophysicists attribute to dark matter, without invoking any unseen particles. In his equations, the additional gravitational pull observed in galaxies arises naturally from the entropic behavior of space-time information. Gravity strengthens where the flow of information slows, just as time slows near massive objects in relativity. This connection between information and time offers a new way to think about the arrow of time itself. In classical physics, time flows because entropy increases. In Verlinder's physics, entropy increases because information seeks equilibrium. The drive toward equilibrium creates both the arrow of time and the illusion of gravitational force. Remove that drive, and both disappear. This raises a profound question. If gravity and time are both emergent, what underlies them? What is the fundamental reality from which information, entropy, and curvature all arise? Some physicists suggest that quantum entanglement, the mysterious connection that links particles across space, could hold the key. Entanglement determines how information is shared between regions of space, and its structure might define the very fabric of spacetime. In that case, time and gravity could emerge together from the evolution of entanglement. When entangled quantum states change, information rearranges itself, entropy grows, and time's arrow appears. The curvature of spacetime and the pull of gravity would be macroscopic reflections of that microscopic quantum process. This idea points toward a unifying vision, that the universe is fundamentally informational. Space, time, and gravity are secondary effects, arising from how information interacts and evolves. The laws of physics are the rules governing that evolution, ensuring consistency as the cosmic story unfolds. If this view is correct, then gravity is not the force that holds the universe together. It is the manifestation of the universe's memory, the way time records the history of information's rearrangement. Gravity bends space, but it is time that gives those bends meaning. In this emerging picture, the future of physics may not lie in discovering smaller particles or deeper forces, but in understanding how information gives rise to the flow of time and the geometry of the universe. Gravity may not be pulling us down at all. It may be guiding us along the natural unfolding of time's information. The next step in this journey leads us to the edge of that unfolding, to a place where time itself falters, the event horizon of a black hole. There, gravity reaches its ultimate strength, and time slows to its breaking point. To see why gravity depends on time, we must see what happens when time dies. At the threshold of a black hole, the universe reveals the most intimate connection between gravity and time. Nowhere else does space-time stretch so far or bend so deeply. As one approaches the event horizon, time's flow weakens, decelerating under gravity's relentless hand. For an observer far away, the process seems endless. Light emitted from the infalling matter grows redder, its frequency dropping lower and lower until it fades into nothingness. To the distant eye, the object never truly crosses the horizon. It merely slows, suspended forever at the edge of time. Yet for the falling object itself, the story is completely different. To it, time flows normally. The crossing of the event horizon happens in a heartbeat. There is no sudden stop, no infinite drag. The object continues inward, descending through a region where space and time begin to trade identities. Inside the horizon, the direction we call time points inward, toward the singularity. Movement through space becomes inevitable motion through time. Gravity becomes not a force pulling downward, but the very shape of time's progression. The event horizon is, in many ways, the place where time dies. To an external observer, nothing ever escapes it, and nothing within can communicate outward. The horizon is a boundary between two realities, one where time flows and one where it halts. It is also a thermodynamic surface, rich with entropy and temperature. According to Hawking's calculations, a black hole radiates energy as if it were a hot object, slowly evaporating over unimaginable spans of time. The deeper the well of gravity, the slower the internal flow of time, and the lower the temperature of that radiation. The black hole's entropy is proportional to the area of its horizon, not its volume. That fact alone carries extraordinary meaning. It suggests that all the information about the black hole's interior is encoded on its surface. What lies within, the region where time itself collapses, is described entirely by data inscribed on the horizon. This discovery was the seed of the holographic principle, the idea that the entire universe may operate in a similar way, with its three-dimensional reality projected from information stored on a distant two-dimensional boundary. Inside a black hole, time's behavior becomes nearly incomprehensible. The curvature of space-time grows so immense that all paths lead inward. There is no way to pause, to reverse, or to escape. Every direction in space points toward the same fate, the singularity. For an infalling observer, time continues normally until that final instant, but from the outside, time for them has already stopped. This duality is not a contradiction. It is a reflection of relativity's deepest truth. Time is not absolute. It depends entirely on perspective. If we imagine freezing the entire universe at once, stopping every clock, halting every vibration, gravity would cease instantly. Without the flow of time, the curvature of space-time could no longer express itself. Gravity is a dance performed on the stage of time, and if the music stops, the dance ends. The event horizon marks the point where that music fades into silence. This realization gives new significance to the phrase, the death of time. The horizon is not merely a physical boundary, it is a temporal one. Beyond it, our familiar ordering of past, present, and future collapses. The direction of time, which gives meaning to motion and causality, becomes meaningless. In the deepest interior, the singularity represents the ultimate endpoint of time's journey, a place where all histories converge and all futures vanish. To the universe outside, the black hole stands as a monument to time's fragility. It is the place where gravity triumphs because time fails. The stronger gravity becomes, the slower time flows. The ultimate expression of gravity's strength is the complete cessation of time. This is not just poetic symmetry, it is physical law. The geometry of space-time demands it. The Einstein equations describe the curvature produced by energy, but when that curvature becomes infinite, the equations themselves break down. Time, like matter, ceases to have definition. For this reason, black holes serve as natural laboratories for understanding how gravity and time intertwine. They expose the limits of general relativity and hint at the need for a deeper theory, one that unites gravity with quantum mechanics. Quantum physics insists that nothing is ever truly lost, not even information. Yet if time stops inside a black hole, what happens to the information carried by the matter that falls in? Does it vanish with time itself? Or is it somehow preserved on the horizon, encoded in the subtle ripples of space-time? This puzzle, known as the black hole information paradox, has driven decades of research. One proposed solution is that information never disappears, but becomes imprinted on the event horizon, scrambled into a chaotic pattern that is slowly released through Hawking radiation. If that is true, then time and gravity cooperate to conserve the universe's memory, even in places where time itself seems to end. The black hole becomes not a grave for information, but a library written in the language of entropy. In this way, the event horizon can be seen as the ultimate meeting point of gravity, time, and information. It is where time's flow stretches to infinity, where gravity reaches its peak, and where entropy records every transformation. The horizon marks the boundary between the known and the unknowable, the visible universe and the hidden one beyond. As one contemplates this boundary, it becomes difficult to separate time from gravity at all. They seem to be two sides of a single phenomenon, two expressions of the same underlying reality. Time flows differently because spacetime curves, and spacetime curves because time flows differently. The horizon is simply the place where this relationship becomes extreme, where time's flow can no longer sustain the geometry it once defined. To move deeper into this mystery, we must ask whether gravity's dependence on time is absolute. Could there exist a state of the universe in which time itself is absent, yet some vestige of gravity remains? To explore that possibility, we must step beyond relativity and into the domain of quantum gravity, where spacetime may no longer be continuous but quantized, broken into discrete chunks of area and time. There, gravity and time may emerge together from the same quantum foundation, not as separate entities, but as inseparable aspects of the same fabric. In the next chapter, we will explore that quantum realm. We will see how theories like loop quantum gravity and the Wheeler-DeWitt equation challenge our very notion of time, describing a universe that exists without motion or change, a timeless cosmos in which gravity and time are not given but constructed. Only by understanding that deeper layer can we begin to answer whether gravity exists because time exists, or whether both are the reflections of something even more fundamental. When Eric Verlinde introduced the idea of emergent gravity, he proposed something that felt almost heretical to traditional physics, that gravity is not fundamental. It is not a force in the same sense as electromagnetism or the strong interaction. Instead, it arises from the deep structure of information and time itself. In this vision, the geometry of spacetime, its curvature, its slopes, its pulls, is the visible echo of how information rearranges as time flows. Verlinde's argument begins with entropy. He imagined that every region of spacetime carries information about the matter and energy within it, encoded like data on an invisible holographic surface. When matter moves, the amount of information accessible to the universe changes. The universe responds to that shift by adjusting its geometry to maximize entropy. The result of that adjustment is what we perceive as gravity. In other words, matter does not fall because it is being pulled by some hidden force. It moves because the universe is always seeking balance in the distribution of information. The fall of an apple, the orbit of a planet, the slow drift of galaxies, all are the natural consequences of spacetime's drive toward equilibrium. The direction we call down is the direction in which information can be most efficiently rearranged. This concept reshapes everything we thought we knew about time. In Verlinde's framework, time is not an independent backdrop. It is the mechanism by which information evolves. Each tick of a clock corresponds to a change in the universe's information content. Without that progression, entropy could not increase and gravity could not manifest. Time and gravity are two sides of the same informational coin. Imagine spacetime as a vast ocean of microscopic information bits, tiny quantum states that together define the geometry of reality. When energy flows through this ocean, it disturbs the information field. Those disturbances spread outward as changes in entropy, shaping the flow of time itself. The ripples in that information ocean are what we interpret as curvature, motion, and attraction. In this view, the speed at which time flows is not uniform. It depends on how information is organized. Where information is dense, near massive objects, time slows. Where it is sparse, time flows freely. Gravity's strength, then, is proportional to the unevenness of information's distribution. When you stand on the surface of Earth, the atoms beneath your feet encode vast amounts of information. That density slows time compared to the empty sky above you, and your motion through the resulting gradient gives rise to the sensation of weight. Entropy and information define not only the shape of time, but its direction. The second law of thermodynamics tells us that entropy tends to increase. This increase is what gives the universe an arrow of time, a sense of forward motion. Gravity acts as the spatial reflection of that temporal arrow. It is the way the universe translates the increase of entropy into geometry. To make this connection vivid, imagine a simple system, a particle floating in space. According to Verlind's model, as the particle moves, the information stored in the surrounding spacetime changes. The universe continually updates its information to reflect the new configuration, ensuring that entropy grows. The particle follows the path of least resistance in this information landscape, sliding toward higher entropy. That path is what we call a gravitational trajectory. This approach also explains why gravity is universal. Every physical object carries information, and all information contributes to the entropy of space-time. There is no distinction between the way light, matter, or energy interact with this structure. All obey the same informational laws. In this sense, gravity is not a force acting on matter. It is the global bookkeeping of how time and information evolve together. What makes Verlander's idea so powerful is that it bridges Einstein's geometry with thermodynamics and quantum theory. It merges the smooth curvature of relativity with the statistical behavior of entropy. The result is a single picture in which space, time, and gravity are not fundamental ingredients of the cosmos, but emergent features of something deeper, the flow of information through time. When we look at the night sky, we are not seeing emptiness sprinkled with stars. We are seeing the visible pattern of an invisible process. Each galaxy, each cluster, each filament of cosmic web is a region where information has condensed into structure, slowing the flow of time and shaping gravity's contours. The vast dark regions between them are places where time flows faster, where information density is low. The entire universe is a living map of information and time in constant negotiation. In this informational picture, gravity and time are not just connected, they are identical in origin. The geometry we see is a mirror of time's uneven flow, and that flow itself is the evolution of information. If we could somehow halt time, every information process would stop. Entropy would freeze. The geometry of space-time would flatten. Gravity would vanish. To think of gravity this way is to see it not as the glue that holds the universe together, but as the memory of its ongoing change. Every curve of space-time records the past movement of energy and information. Every tick of time carries forward that record, rewriting the geometry as it goes. The universe does not exist in time. It is time, continuously self-updating. This understanding leads to a striking conclusion. Gravity does not merely depend on time. It is time, seen through the language of curvature and motion. The shapes we see in the cosmos, the bending of light, the spirals of galaxies, the falling of stars, are the handwriting of time on the page of space. If this is true, then the deepest question in physics is not what causes gravity, but what causes time to flow. For wherever time flows, gravity follows, and wherever gravity grows, time bends. They are not two phenomena, but one story told in two dialects, the story of the universe remembering itself. There is no place in the universe where the link between gravity and time becomes more evident than at the edge of a black hole. Here, space-time stretches to its breaking point. The event horizon is not a wall or a surface you could touch. It is a boundary in the flow of time, a place where seconds slow until they nearly stop. It is the frontier between motion and stillness, between history and silence. As an object approaches this horizon, something remarkable happens. To a distant observer, the object's clock begins to run slower and slower. Its light becomes redder, its image fainter. From far away, it seems to freeze in place, never quite crossing that final threshold. Time for the falling object appears to halt, caught forever in gravity's grip. But for the object itself, nothing unusual occurs. It continues its journey inward, crossing the horizon in finite time, unaware that to the rest of the universe, it has vanished. This paradox, time stopping for one observer and flowing normally for another, reveals the deep relativity at the heart of gravity. It shows that time's flow is not a universal rhythm, but a local one, shaped by the curvature of space-time. Near a black hole, that curvature becomes so extreme that it divides reality into two disconnected worlds, one where time continues and one where it ends. Inside the event horizon, the geometry of space-time changes character. The direction we call inward becomes the direction of time itself. To fall toward the singularity is not to move through space, but to move inevitably forward in time. Escape is impossible because escaping would require moving backward in time, and that is forbidden by the very structure of space-time. The singularity is not merely a point of infinite density, it is the final destination of time's arrow. From the outside, this transition is invisible. The black hole's horizon hides its interior completely. No signal can return, no message can cross outward. To the external universe, the horizon marks the death of causality. Yet paradoxically, the horizon is also alive with activity. Quantum effects near its edge give rise to Hawking radiation, a faint glow of energy that leaks away as the black hole slowly evaporates over unimaginable spans of time. That radiation reveals something astonishing. The horizon has temperature and entropy. It behaves like a thermodynamic system. The entropy of a black hole is proportional to the area of its horizon, not its volume. This simple but profound fact suggests that all the information about everything that has ever fallen into the black hole is stored not inside it, but on its surface. The horizon becomes a cosmic ledger, a perfect record written in the language of time and information. What happens to the information inside? This is one of the greatest mysteries in modern physics. If information truly disappears beyond the horizon, then the fundamental laws of quantum mechanics, which insist that information is never lost, would be broken. Yet if information is somehow preserved, it must be encoded in the subtle fluctuations of the horizon itself. The surface of the black hole, rippling with quantum uncertainty, may hold the memory of all that has ever crossed it. This tension, the clash between general relativity's silence and quantum theory's insistence on memory, has become the focus of the black hole information paradox. The leading idea is that information is not destroyed, but scrambled, hidden in the correlations of Hawking radiation as it escapes. Over eons, that radiation carries away the black hole's mass and entropy, slowly releasing the encoded information back into the universe. If that is true, then the horizon is not the death of time, but its slow transformation into information. Seen this way, a black hole is not an abyss, but a process, a cosmic engine converting time into geometry, geometry into entropy, and entropy back into time. The stronger the gravity, the slower the clock. The slower the clock, the steeper the curve of space-time. At the horizon, this curve becomes infinite, and time itself flattens into stillness. But even in stillness, information moves, whispering across the surface as quantum vibrations. Time does not vanish entirely, it changes form. For an outside observer, the black hole lives forever, suspended at the edge of time. For the matter within, existence continues only for an instant before being crushed into the singularity. Two descriptions of the same event, both true, both incomplete. This duality is the ultimate expression of relativity. Time depends on where and who you are. In this strange symmetry, we see the truth that has been forming since Einstein first curved space with time. Gravity is not the cause of time's distortion, it is the distortion. The closer you come to infinite gravity, the closer you come to the end of time. The two die together. Black holes, then, are not just exotic astrophysical objects. They are mirrors reflecting the deepest structure of the cosmos. They show that gravity's strength is a measure of time's weakness, that when time stops flowing, gravity stops being gentle and becomes absolute. The event horizon is not merely a border in space, it is the edge of becoming, the final intersection of energy, entropy, and time. If the laws of physics hold true, the black hole will eventually evaporate, releasing its stored information back into the cosmos. Time will reclaim what gravity once froze. The universe, in this grand cycle, shows us that nothing truly ends, only transforms. Time slows, halts, and then begins again. And yet, if time and gravity are so inseparable, one question remains. If gravity depends on time's flow, what happens in a universe where time has no meaning at all? Could gravity exist before time, or do they rise together from some deeper, timeless reality? To find the answer, we must step beyond black holes and into the quantum realm, where the flow of time itself begins to blur, and where gravity might emerge not from geometry or entropy, but from the statistical behavior of quantum spacetime. At the smallest imaginable scales, spacetime ceases to behave like the smooth continuum Einstein described. It trembles, flickers, and pulses with uncertainty. Physicists call this domain the Planck scale, where distances are about 10 to the power of minus 35 meters, and times are about 10 to the power of minus 44 seconds. Here, gravity and time begin to blur into one another, and the familiar flow of cause and effect dissolves into quantum haze. In classical physics, spacetime is a fabric, but in quantum gravity, it may be a network, a web woven from discrete quanta of space and time. The theory known as loop quantum gravity proposes that spacetime itself is made up of finite loops of information, forming an intricate spin network that vibrates and changes as the universe evolves. In this view, geometry is not continuous, but granular. Area, volume, and even time come in indivisible units, like the pixels of reality. Within this quantum structure, gravity becomes a statistical effect. It is not a smooth field, but an average outcome of countless microscopic fluctuations in space-time geometry. Each fluctuation represents a tiny change in how time and space relate, and when trillions upon trillions of them are combined, the result is the curvature Einstein described. Gravity, then, is not fundamental. It is emergent, like temperature arising from the motion of atoms. This analogy is more than poetic. Temperature does not exist at the level of a single particle. It emerges from the collective behavior of many. In the same way, gravity may not exist at the level of individual quantum events. Only when we step back far enough do the random fluctuations average into a coherent geometry. That geometry carries curvature, and curvature is what we call gravity. If this is true, then time itself may also be statistical. Just as gravity arises from averaged curvature, the flow of time might arise from the collective synchronization of quantum events. The familiar arrow of time could emerge from the way these microscopic processes become correlated. The ticking of a clock, the orbit of a planet, even the decay of a particle, all might be manifestations of quantum correlations aligning into a macroscopic rhythm. Quantum field theory already hints at this connection. It describes the universe not as a collection of particles, but as vibrations in underlying fields that pervade all of space. Every particle is a ripple in these fields, and every force is the exchange of energy between them. But these interactions take place in time, and without time, the equations lose meaning. Quantum theory depends on time's existence to define motion. energy, and probability. Without time, there is no evolution, only a static wave of potential. This dependence suggests that gravity, which emerges from spacetime itself, could not exist without time. The two are inseparable, even at the quantum level. When physicists quantize gravity, attempting to merge it with quantum mechanics, they must also quantize time. The two must rise together from the same microscopic foundation. The gravitational waves detected by observatories like LIGO and Virgo are macroscopic evidence of this quantum dance. They are ripples in the very fabric of spacetime, produced when massive objects like black holes or neutron stars collide. But those ripples are not smooth. They carry faint imprints of the underlying quantum granularity. Each wavefront is the sum of countless tiny oscillations of spacetime itself, each one a whisper from the quantum world. These waves show that spacetime can flex and vibrate, and that gravity behaves like a field of energy. But they also confirm that time is the medium through which those vibrations propagate. Without the continuous progression of time, no wave could move, no energy could flow, and no gravity could ripple. Time and gravity are the same phenomenon, expressed in two directions. Gravity curves space, while time carries that curvature forward. Loop quantum gravity goes even further. It predicts that at the smallest scales, spacetime becomes foamy, a sea of ever-changing geometries. Within this foam, what we call past and future lose distinction. Events do not occur in sequence. They exist in superposition, overlapping like chords in a song. The flow of time we experience emerges only when we zoom out far enough to see order in the chaos. If that is the case, then gravity may be the memory of time's coherence. It is the pattern left behind when quantum fluctuations align into a consistent direction of flow. In a perfectly random universe, there would be no gravity and no time, only timeless noise. But the universe is not perfectly random. It carries an asymmetry, a faint arrow that points from order to disorder, from beginning to end. That asymmetry gives rise to both entropy and curvature, to both time and gravity. This insight offers a glimpse of unity. Gravity and time are not two separate fabrics woven together, but one emergent tapestry. Each fold of space is a trace of time's uneven passage. Each tick of time is the evolution of space's geometry. They are born from the same quantum conversation, and neither can exist without the other. But if this is so, then the question deepens. What happens in a universe where time has no direction, where the arrow of entropy is gone and quantum processes no longer evolve? Does gravity still exist when there is no change to give it meaning? To explore that, we must imagine the unthinkable, a cosmos without time at all. Imagine a universe where clocks do not tick, where motion does not unfold, where past and future dissolve into the same eternal now. In such a cosmos, there is no flow, no before or after, only existence, frozen and complete. It sounds like a philosophical abstraction, but deep within quantum gravity lies an equation that describes exactly this scenario. It is called the Wheeler-DeWitt equation, and it has no time variable at all. The Wheeler-DeWitt equation treats the universe not as something that evolves, but as something that simply is. All possible configurations of space, matter, and energy exist simultaneously in what physicists call configuration space. There is no moment when one configuration becomes another. The entire history of the universe, past, present, and future, is contained within this single timeless structure. This picture challenges everything we intuitively understand about reality. We experience time as motion, change, and sequence. Yet in this timeless formulation, nothing ever changes. The flow of time, and with it the phenomenon of gravity, appear to be illusions, emerging only when an observer experiences a limited portion of the total universe. To understand how this works, imagine the universe as a film reel. Each frame is a complete image of reality at one instant. The Wheeler-DeWitt equation describes the entire reel as a single object. every frame already exists. What we perceive as time passing is the mind's traversal from frame to frame. Gravity, which depends on differences between frames, would not exist without that traversal. It is born from the comparison of one configuration to the next. In a timeless universe, there is no curvature of space-time, because there is no time to curve. The Einstein field equations, which relate geometry to energy, depend on the existence of a time dimension. Without time, acceleration loses meaning and gravity ceases to operate. The geometry becomes static, a frozen landscape of potential, where nothing falls, bends, or evolves. Yet, this does not mean such a universe would be dead. It would contain every possible event simultaneously, like an infinite sculpture of all history at once. Our experience of time, our sense of moving through it, would be akin to tracing a single thread through that sculpture, constructing the illusion of motion from stillness. Physicists such as Carlo Rovelli have explored this idea deeply in loop quantum gravity. Rovelli argues that time is not fundamental, but relational. It exists only through change, the comparison between states. When one part of the universe alters relative to another, time is born. Without relationships, there is no time. Without time, there is no gravity. The two arise together as the universe begins to differentiate itself. In this light, the early universe may not have begun in the temporal sense. Instead, time itself may have crystallized out of a timeless quantum state. The Big Bang, rather than being a moment in time, might have been the emergence of time. Before that, there was no before. Space, time, and gravity unfolded together as the universe cooled and symmetry broke. The Wheeler-DeWitt equation's timeless universe is not a cold void, but a profound statement. Reality may be static at its core, with time and gravity emerging only when complexity appears. Entropy, the measure of disorder, gives time its arrow. As entropy grows, time flows. As time flows, gravity shapes space. Remove entropy, and you remove time. Remove time, and gravity fades into stillness. In this vision, gravity and time are both approximations. Useful, beautiful illusions arising from deeper, timeless laws. The curvature of space-time, the ticking of clocks, even the expansion of the cosmos are secondary effects, like shadows cast by something more fundamental. The true universe might be timeless information, and what we experience as reality could be the story that information tells itself. This perspective brings a strange comfort. If all times coexist, then nothing is ever truly lost. Every moment, every life, every thought already exists somewhere in the grand structure of the timeless universe. We are simply traveling through it, guided by the flow of time that gravity makes visible. And so, the question changes. Instead of asking, does gravity exist because time exists? We might ask, does time exist because gravity gives it shape? Or perhaps neither exists on its own. Perhaps both are born together, entangled in a deeper layer of quantum reality. To explore that final mystery, we turn to the frontier where quantum physics meets space-time geometry, the realm of entanglement, where the very connectivity of the universe gives rise to both time and gravity together. At the deepest level of the universe, beneath the quantum foam, and beyond the reach of even the finest mathematical tools, there exists a strange kind of order, one that does not depend on distance or geometry, but on connection. This is quantum entanglement, the invisible thread that binds particles together, so that the state of one instantly influences the state of another, no matter how far apart they are. In the 1990s, Juan Maldacena proposed the holographic principle, a revolutionary idea suggesting that all the information contained in a region of space can be described by data encoded on its boundary. This was the foundation of the ADS-CFT correspondence, where a universe with gravity in higher dimensions is equivalent to a universe without gravity on a lower dimensional surface. Later, physicists like Mark van Ramsdonk took this idea even further, proposing that spacetime itself emerges from patterns of entanglement. In that framework, geometry is not fundamental. It is the manifestation of how quantum information is entangled. The more two regions of the universe are entangled, the closer they appear in space. If entanglement decreases, distance increases. When entanglement breaks entirely, space-time itself tears apart. Space, in other words, is nothing but the visible map of invisible quantum relationships. If entanglement gives rise to space, then time emerges when those entanglements evolve. Time is the process of quantum information changing its pattern of connection. The flow of time, as we experience it, is simply the unfolding of quantum entanglement across the universe. Gravity, in this view, is the curvature produced by that unfolding. Think of the universe as a grand network, with each node representing a quantum system and each link representing entanglement. As the network evolves, the pattern of links shifts, and this reconfiguration defines both the geometry of space and the progression of time. When entanglement increases in one region, space-time curves inward. When it decreases, space-time expands. Gravity, then, is the geometric echo of quantum entanglement evolving through time. This means that time and gravity are not separate phenomena at all. They are two aspects of the same underlying process, the rearrangement of information. When entanglement changes, time flows. When time flows, space-time curves. Without change in entanglement, there is no time. Without time, there is no gravity. This idea bridges the largest scales of the cosmos with the smallest scales of quantum mechanics. It explains why general relativity, which describes gravity, and quantum field theory, which describes the microscopic world, might ultimately be compatible. Both are languages for describing how information organizes itself. Relativity is the large-scale grammar of that organization. Quantum mechanics is the syntax beneath it. To visualize this, imagine two particles that are entangled. Their connection defines a kind of microscopic bridge, a thin thread of space-time connecting them. When multiplied across countless particles, these threads weave together the smooth continuum we call space. If one region of this web becomes more entangled, the threads draw tighter and space-time curves. Gravity is not the pull of mass, but the tightening of those threads as information reorganizes itself. This picture even provides a new way to think about black holes. The event horizon, which marks the boundary of no return, is not a surface of destruction, but a region where entanglement reaches its maximum limit. All the information that falls into a black hole becomes entangled with the horizon's quantum degrees of freedom. The geometry of the horizon, its area and curvature, is a direct reflection of that entanglement structure. As the black hole radiates energy through Hawking radiation, the entanglement shifts, slowly releasing the stored information back into the universe. Time in that process is the gradual reconfiguration of those quantum links. Thus, gravity, time, and information form an inseparable triad. Each gives rise to the others. Entanglement shapes geometry. Geometry defines how time flows. Time governs how entanglement evolves. It is a closed, self-consistent cycle, a cosmic feedback loop. This vision also reframes the concept of causality. In our everyday experience, cause precedes effect, and time flows in one direction. But in the quantum universe, entanglement can link events without obeying a simple sequence. Past and future may not be distinct, but interconnected through deeper informational relationships. The apparent linearity of time may be a large-scale illusion, a macroscopic consequence of how entanglement statistically arranges itself. In this sense, both time and gravity are emergent illusions, born from the same quantum foundation. We experience them as separate because we live within the macroscopic world they create. But from the universe's deepest perspective, there is only information, entangled, evolving, and self-aware through its own structure. If this is true, then to understand time is to understand gravity, and to understand gravity is to understand the flow of information itself. The universe is not a collection of particles in motion through time. It is a self-entangled quantum system that experiences itself as motion. Every sunrise, every orbit, every gravitational wave is the universe updating its own state. The curvature of space-time is the record of those updates. Time is the rhythm by which they occur. And so, the question that began this journey, does gravity exist only because time exists, begins to reveal its answer. Time and gravity are not two separate realities, but one continuous phenomenon. They are the twin languages of entanglement. The universe curves not because of mass, but because information evolves. It flows forward not because of clocks, but because entanglement deepens. From this perspective, every moment of time is an act of creation, and every gravitational curve is the shape of that creation written into geometry. The universe is not just a story told in time, it is time, writing itself into space. From the moment Einstein saw that gravity was not a force but the curvature of space-time, physics has been on a long journey to uncover what that curvature truly means. Each discovery since then, Minkowski's four-dimensional continuum, Jacobson's thermodynamic spacetime, Verlinder's emergent gravity, Maldaceno's holographic universe, has pointed toward one conclusion. Gravity and time are not separate entities. They are two expressions of the same underlying flow, the same universal rhythm by which information becomes reality. If gravity is the bending of space-time, and space-time itself is the geometry of time's flow, then to speak of gravity is to speak of time made visible. The universe does not fall through space, it falls through time, and that fall is what we perceive as curvature, as motion, as attraction. Every object, every particle, every star is caught in that flow. Matter does not pull on other matter across distance. It simply moves along the natural direction of time within curved space-time. Where time flows faster, matter drifts away. Where time flows slower, matter gathers. Gravity, in this sense, is the pattern created when time's flow becomes uneven. This unevenness drives everything we know. It shapes the orbits of planets, the clustering of galaxies, even the expansion of the cosmos itself. The entire universe is an ocean of time currents, and matter rides those currents like leaves on a cosmic tide. Entropy gives time its direction, but gravity gives it form. Time would have no texture, no structure, if not for the way gravity bends it. And gravity would have no meaning without the constant unfolding of time. They are partners in an endless conversation, one that began with the universe and will not end until it returns to silence. When we look up at the night sky, what we are seeing is time made visible. The light from distant galaxies has traveled for billions of years to reach us, crossing the warped geometry of space-time. Each photon's path is curved not by invisible forces, but by the very flow of time itself. The cosmos is not static, it is the living map of time in motion. The deeper we study the universe, the clearer this truth becomes. Black holes show us that gravity reaches its greatest strength when time slows to a crawl. Quantum mechanics shows us that even the tiniest fluctuations of space-time depend on the existence of time. Thermodynamics shows us that without the arrow of entropy, gravity would lose its direction. Entanglement shows us that geometry and time emerge together from the same informational network. Together, these threads weave one consistent picture. Time and gravity are not separate fabrics, but the same tapestry viewed from different angles. One shows us the flow, the other the form. One defines becoming, the other defines being. The universe cannot have one without the other. If time were to stop, gravity would vanish. The stars would no longer curve space, light would no longer bend, and matter would no longer fall. Geometry would freeze into perfect symmetry, unchanging, indifferent, empty. Without time, there would be no curvature, no motion, no memory. But the universe does not stop. It remembers. Every gravitational wave, every orbit, every falling stone is that memory in motion. Gravity is the handwriting of time upon the cosmos. And time is the voice of gravity speaking through the curvature of space. This unity reveals a profound simplicity hidden beneath all complexity. Everything that happens, every heartbeat, every explosion, every thought, is a manifestation of time's uneven flow through the geometry of space-time. Gravity does not act upon matter. It gives matter a stage on which to act. Time does not carry events forward. It allows them to exist at all. At the deepest level, the universe is not made of matter or energy. It is made of relationships, of information continually evolving. Time measures that evolution. Gravity shapes it. The two together form the dynamic architecture of existence. Perhaps this is the final symmetry Einstein was reaching toward but never fully saw. That time and gravity are not companions but reflections, two faces of the same cosmic truth. Remove one, and the other ceases to be. Keep both, and the universe sings its eternal song of motion and change. So the question, does gravity exist only because time exists, finds its answer not in equations, but in the nature of experience itself. Without time, there is no curvature, no fall, no cause or effect. Gravity is time, written in the language of space. The universe bends, not because it must, but because time flows. Stars collapse, galaxies swirl, and light curves not under a mysterious pull, but along the shape that time carves through the cosmos. And when you stand on the surface of the earth, feeling its gravity beneath your feet, you are not being pulled down by an invisible force. You are simply following the natural slope of time, falling through the geometry of your own becoming. Perhaps that is the greatest revelation of all. Gravity bends space, but it is time that gives it meaning. Without time, no motion. Without motion, no life. Without life, no witness to the universe's beauty. Maybe then, gravity is not just the curvature of space-time. It is the universe remembering itself, moment by moment, curve by curve, second by second. It is time, seen through the lens of mass.